In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about tutorial model water purification reactor. Water purification is a multiple step process for turning natural water into drinking water. At least one step must be a disinfectant step. One way to achieve efficient disinfection in an environmental friendly way is to use ozone. A typical ozone purification reactor is about 40 meters long and resembles a maze with partial walls or buffers that divides the space into room-sized compartments. When water flows through the reactor, turbulent flow is created along its winding path around the baffles towards the exit pipe. The turbulence mixes the water with ozone gas, which enters through diffusers just long enough to deactivate micropollutants. When the water leaves the reactor, the remaining purification steps filter off or otherwise remove the reacted pollutants. When analyzing an ozone purification reactor, the first step is to get an overview of the turbulent flow field. The result from the turbulent flow simulation can then be used for further analysis of residence time and chemical species transport and reactions. This step requires adding more physics features to the model. The current application solves for turbulent flow in a water treatment reactor using the turbulent flow capsule interface. The model geometry along with some boundary conditions is shown in figure 10. The full reactor has a symmetry plane which is utilized to reduce the size of the component. The domain equation and boundary conditions section. Based on the inflow velocity, which is 0.1 meter per second, and a length scale L equal to the diameter of the inlet, the Reynolds number is equal to U multiplied by L divided into V, which is equal to 0.1 multiplied by 0.4 divided by 1 multiplied by 10 to the power of minus 6, which is equal to 4.10 to the power of 5. Here V is the kinematic viscosity. The high Reynolds number clearly indicates that the fluid is turbulent and the turbulence model must be applied. In this case, you will use the capsule model. It is commonly used in industrial applications because it is both relatively robust and computationally inexpensive compared to more advanced turbulence models. One major reason to why the capsule model is inexpensive is that it employs wall functions to describe the flow close to the walls instead of resolving the very steep gradients there. All boundaries are walls in figure 10 except in the inlet, the outlet, and the symmetry plane. The fully developed flow option is used as an inlet boundary condition. A constant pressure is prescribed on the outlet. Notes about the implementation. A three-dimensional turbulent flow can take a rather long time to solve, even using a turbulence model with wall functions. To make this tutorial feasible, the mesh is deliberately selected to be relatively coarse and the results are hence not mesh independent. It is good practice to investigate the effect of refining the mesh in order to ensure that the model is well resolved. The results section. The velocity field in the symmetry plane is shown in the figure 11. The jet from the inlet hits the edge of the first baffle, which splits the jet. One half creates a strong recirculation zone in the first chamber. The other half continues downstream into the reactor and gradually spreads out. The velocity magnitude describes as more fluid is entrained into the jet. The figure 12 gives a more complete picture of the mixing process in the reactor. The streamlines are colored by the velocity magnitude and their widths are proportional to the turbulent viscosity. Wide lines hence indicate a high degree of mixing. The turbulence in this model is mainly produced in the shear layers between the central jet and the recirculation zones. The mixing can be seen to be relatively weak near the entrance to the reactor and to increase further downstream. And the reference is the Hoffman and his colleagues. The article number is the use of the CFD modeling to determine the influence of residents' time distribution on the disinfection of drinking water in ozone contactor. Beta comes to conference 2007, Grand Nobel, and I want to go to the model wizard. The first step to build an application is to open Console Desktop, then select the physics interface and specify the type of analysis you want to do. In this case, a stationary turbulent fluid capsule analysis. The first step is to open the Console Multiphysics. On the new page, click Model Wizard, then click the three-dimensional button. The second step is that in the Select Physics tree under the Fluid Flow, select the single phase flow, then select the turbulent flow and click Turbulent Flow Capsule for SPF. The third step is click Add and then click the Study button. The fourth step is in the tree under General Studies, click Stationery. The fifth step is click the Down button. The global definitions parameters. The first task is to define a parameter for the inlet velocity. Parameters can be used to run parametric studies. The first step is in the Home toolbar, click Parameters and select parameter LPI. The Home toolbar refers to the specific set of controls near the top of the desktop. The second step is go to the Settings window for parameters. In the table, enter the following settings. The first, in the Name text field, enter you underline in, and the next one is in the expression text field enter the 0.1 meter per second, and the third one is in the description text field enter inlet velocity. And what about the geometry? You can build the reactor geometry from geometric primitives. Here instead use a file containing the sequence of geometry features that has been provided for convenience. The location of the file used in this exercise varies based on your installation. For example, if the installation is on your hard drive, the file path might be similar to C program files comes to Console 64 multiphysics applications. The first step in the geometry toolbar, click Insert Sequence. The second step is browse to the application library folder and double-click the file. Safety module, single phase flow, water purification reactor, geom sequence.mph. The third step in the home toolbar, click Build All. The geometry sequence is now inserted into your component and should look like the figure below. And what about the material section? In the Home toolbar, click Add Material, then go to the Add Material window. In the tree under Built-in, click Water Liquid, then in the Add Material window, click Plus, Add to the component. In the Home toolbar, click Add Material again to close the window. The physics properties are now available for safety simulation. The next step is to specify the domain and boundary conditions. Turbulent fluid epsilon. The fluid properties L node species and the domain emotion equations, and by default uses the material properties specified by the water liquid material selected in the previous system. The inlet section in the physics toolbar, click boundaries and choose inlet. The next step is select boundary which represents the inlet. The next step in the setting windows for inlet, locate the boundary condition section. From the list, choose fully developed flow. Locate the fully developed flow section and in the UAV text field type U in. The symmetry section. In the physics toolbar, click boundary and choose symmetry. Select boundary tree only and the outlet. In the physics toolbar, click boundaries and choose outlet. The second one is the select boundary 28 only. The sequence of nodes in the model builder under turbulent flow capsule should match the figure. The D in the upper left corner of node means it is a default node. All boundaries not selected in inlet, symmetry, or outlet now have the default wall condition. And what about the mesh chapter? The physics-induced mesh automatically introduces a mesh that is a bit finer on the walls than the free stream mesh. It also refines the mesh at sharp corners and adds a boundary layer mesh. The finer mesh on the walls is not critical in this model since most of the turbulence is produced in the shear layers between the jet and recirculation zone. The boundary layer mesh can also be coarsened in the order to save computational time. The first step is in the model builder under components, click mesh. Then in the setting windows for mesh, locate the physics control mesh section. From the element size list, choose cursor. The size to go to the mesh toolbar and click edit. A mesh sequence as shown below appears. It contains suggestions made by the physics interface. This asterisk on each of the mesh features indicates that the features are not yet built. The second step is that right click size 2 and choose disable. Thank you so much for watching my tutorial video until the end, and also you can download the water purification from my github.com/masterscript, and you just need to search the water purification in the address bar, in the search bar. Today is 9th of the March 2026 and time is 7:04 o'clock in the morning.